Okay, everybody. So the plan for today is to start on chapter 4, Systems of Linear Equations. And we'll just start working our way through the first few sections of chapter 4 and see how far we get today. Wrap up these topics next week, next class meeting, and probably start systems of linear equations in 3 variables next time. Note that the Unit 1 exam is next week, this coming week. The material is chapters 1 through 3, with kind of a focus on chapters 2 and 3. So I think there's only one problem on the exam from chapter 1. So most of the material is chapters 2 and 3. I did post a sample exam last night, so that is available on WebAssign. You can take a look at that. That should give you a pretty good idea of what the actual exam is going to be like. I think the Unit 1 exam, it should be pretty smooth. It should be mostly review for a lot of you. So, this shouldn't be a very difficult exam. Unit 2 and 3 might be a little more challenging. Just so that basing your study off of, um, this one for the Unit 2 and 3, you might have to prep a little more for the Unit 2 and 3 exam and for the final exam than you do for this one. As I mentioned before, no Proctor U for the first exam. We've had a couple people that have had some tech issues, and I just want to make sure those are sorted out before we, move into using Proctor U on a high value exam. So just want to make sure that that's all squared away first. And again, for this first exam, it's, a little bit like a kind of a warm-up exam anyway. Very important, though, do not wait until the last minute to take the exam. There are no extensions on exams, so make sure you're familiar with that syllabus policy. So no due date extensions on exams. You will have a full week to take the exam. So from this coming Monday at 9 a.m. through the following Sunday at 11:59 p.m., the exam will be available. So there's plenty of time for you to be able to figure out a time slot in there that works for you and take the exam not at the last minute. And by the last minute, I mean, if you wait till Saturday or Sunday, that's the last minute. Um, by last minute, I mean, if something goes wrong, if you have a power outage or a tech issue or something, have you left yourself enough buffer, enough margin so that you can get anything sorted out that you need to get sorted out? And certainly if it's Sunday evening, probably not. If something goes wrong, you're not going to be able to take the exam and you're going to lose those points. But even Saturday is cutting it kind of close, right? I would recommend that everybody plan to take the exam no later than about Thursday evening. And that way, if something goes wrong, you still have all business day Friday to get in touch with me, to work with the WebAssign folks. If I needed to, I could get in touch with our Cengage rep and, our the tech support from my side at Cengage and get something squared away. But, if we're Saturday night or even worse, like Sunday evening, a lot of those resources aren't going to be available. Or also things like, hey, my internet's, being really wonky right now, not sure what's going on. You can go to a CCAC campus and take the exam. There are resources there as well. But again, you want to make sure to give yourself enough time that you have some time when those other resources are open, CCAC's resources, or maybe a local library, something like that, if you needed it. So again, don't wait until the last minute to take the exam. I recommend no later than Thursday evening planning to take the exam, and that gives you quite a bit of buffer. So any questions? Oh, and I did send out an announcement with quite a bit of detail on it early this morning. So you can refer back to that announcement. You don't have to come back to these videos to see this material again. Just check your email or Blackboard for that. So any questions on anything about the Unit 1 exam?
I do.
Yeah.
Hi. So, is there like a time slot that, or like on the days that we can take the exam? So it has to be like if it's going to be recorded. I know it's not Proctor. You record it, but you're record. So I don't. Is there like specific way? Did I miss that part? I'm sorry.
No, good question. So for this exam, because we're not using Proctor U for this one, because we still have some kinks to work out, there's no proctoring, there's no recording. So it basically will feel like you're just logging on and doing a long homework. So basically you just log on to WebAssign, you'll open the exam, and there's the sample exam that's available now that you have lots of attempts on. But when you open the actual exam, you'll just have to complete that in one setting, and that's really the only restriction. So, um, so there are no time slots, there are no windows. You can take it any time that works best for you in that, Monday at 9 a.m. to Sunday at 11:59 p.m. Um,
Okay.
Available window. Yep.
But when there is a proctor, there's just going to be one specific time
That's
during
one
the
of the
week.
things that I have to look into. Like I said, we switched over to this new system just this
Hmm.
semester, and um, there hasn't been a there hasn't been a ton of support and explanation on exactly how everything works. So my understanding is that because it's the automated system, because there's not going to actually be a person on the other end like watching
Hmm.
or walking you through it. My understanding is that you can take it anytime you want and you don't really need to schedule it, but that's also not made extremely clear. So that's one of the things that we're working to um, figure out before we, really bring this live. And I don't want to put you all in a situation where I say something and then the reality ends up being something different and you're already a little bit stressed for an exam and then that just adds on top of it. So yeah, that's one of the things that we're trying to work out. But as far as I know, at least with Examity for the automated system, you didn't really have to schedule anything in advance.
Okay, thank you.
Yeah, yeah, you're welcome. Yeah. But definitely, for other courses, if there's a live proctoring option, which we're not using in this course, but some other instructors might, if you have to meet up with like a person on the other end, any system that I know of does require you to schedule that, a good bit in advance. I stopped using that because it was just very, very glitchy and unreliable from my experience, but my experience isn't the same as everybody else's. So some folks still do use that. Any other questions on the exam? Okay. The quote of the day today is uh, this idea that velocity is a vector quantity. This is actually from one of my wife's colleagues in St. Louis. Uh, and she would say this meaning that, well, the idea of velocity is that there is a speed and a direction. So kind of, if you're looking to accomplish something, if you just hit the ground running, but you have no idea what direction you're going in, you're probably not going to get a whole lot accomplished. But also if you point yourself in the right direction, but just kind of sit there and do nothing, then you're also probably not going to get a lot accomplished. So um, the way that I kind of think of this idea is it's a little less catchy, but it's that effectiveness, the ability to do something is something like the product of efficiency and effort. So if you put a ton of effort into finding the best way to do something, but you never actually take a step forward and do it, you kind of multiply a big number by zero and you get zero effectiveness. That's kind of my tendency is perfectionist procrastination. I want everything to be perfect before I move forward, and you know that doesn't often work. That doesn't often happen. So we have to put forward a little bit of effort. But again, if you put forward a bunch of effort and you don't have good direction, you're probably not going to get very far either, right? If you're trying to learn a language, you could spend, say, a ton of time researching all of the different resources out there for your language and what's the best way to do this. And you could spend 200 hours figuring out the best way to do it, but never actually, speak one word of the language that you're trying to learn. Or you could just start picking random YouTube videos or random apps or whatever and doing a little bit of this, a little bit of that. And because there's really no direction, there's really no strategy, probably also not going to be very effective. Same kind of thing with, say studying for an exam, like you can make a study plan, but if you spend, 10 hours making a study plan, you might never actually get around to studying, right? And that's not super effective for getting a better score in an exam. On the other hand, you could just kind of sit down and start randomly going through the book and reviewing different stuff, and you're putting in a lot of effort, but that's probably not as high yield for prepping for the exams as it could be if you had, spent 10 or 20 minutes making a study plan to direct your studying. And then more kind of on the career side of things, you could become very effective at something that kind of nobody cares about, right? So if you want to further your career, or whether that's your academic career or your future career, um, the kind of buzzword these days is impact. Like you want to have an outsized impact on your organization. So this means that you want to be effective at something or a couple of things, and you want those things to be relevant, right? So if you're really, really good at, whatever, speaking Spanish, but you are going to work in an accounting firm in Cleveland or something, like, well, is that really relevant to them? You might be really, really good at a certain skill, but is that a skill that's in demand in the field you're looking at going into? Now, to be clear, not everything in our life should be geared towards the perspective of, is this good for my career? So if you want to learn Spanish just because you think it's cool or because you have family or friends who speak Spanish, well, great, but as far as, thinking of what, what can I do to make my career, to push my career forward, we also want to have an eye on relevance. Is this a skill that is marketable, that will set me apart from the other applicants in the pool, or that will bring value to my organization and lead to me getting a promotion, or uh, salary bump, or doing work that is more purposeful to me, or anything along those lines. Okay, so that's the thought for today. So moving into our next topic, starting a new chapter, chapter 4, systems of linear equations. And like I said, we're just going to kind of start working through 4.1, 4.2, and 4.3. I'm not going to delineate them too much because it's really just solving systems and their applications. So we're going to look at a motivating example. Why might we, what's a situation where we might come up with a system of two equations? So suppose that we have access to cooking vinegar, which is 5% acid by volume, let's say, and cleaning vinegar, which is 7% acid by volume. And we want to make a solution, a 30 fluid ounce solution, that is 6.2% acid by volume. So I want to combine these two cooking and cleaning vinegars together to make a solution that is a certain amount of acidity, and I want a certain amount of that solution. How can I figure out how much of the cooking vinegar and how much of the cleaning vinegar I should mix together to get the right amount of a solution with the right acidity? So I have two constraints. One constraint is the amount that I want to have at the end, and the other constraint is the acidity that I want to have at the end. These two constraints naturally lead to two equations. Each equation represents one constraint on the solution space. So we might end up with two equations in two variables, say A and B, where A is the amount of cooking vinegar that we use in fluid ounces, and B is the amount of cleaning vinegar we use in fluid ounces. We might end up with two equations that look like this, and we want to solve these equations. And we'll talk in a minute about what exactly we mean by that. We can also think of, say, reasonability conditions, like, for instance, can I make an 8% solution or a 3% solution on the basis of these? Well, the answer is really no, right? I can't reasonably make an 8 or a 3% solution if I have a 5 and a 7% to mix together. I can really only make solutions that have acidity between 5 and 7%. And I could also think of a situation where I have, like, one solution is 5% acidity, another solution is also 5% acidity. Can I make a solution with 6% acidity? Well, no, if both of my solutions have the same acidity, I can't change the acidity. So there might be no solution in that case as well. Or on the other hand, if I said I have solution 1 that's 5% and solution 2 that's 5%, how much do I have to mix together of each of them to make a solution that's 30 fluid ounces of a 5% acidity solution. Well, there's lots of answers to that, right? I could mix 1 ounce of the first and 29 ounces of the second. That gives me 5% because they're both 5%. I can mix 2 and 28 or 3 and 27 or 3.5 and 26.5, right? I have infinitely many solutions. So we actually see that for these, just by thinking through some different possible scenarios for these systems, these 2x2 systems, so to speak, these systems of 2 equations and 2 variables, we can have one solution, one answer. I keep using the word solution, but we're also using solution to talk about the combined fluids. So, but we could have one answer, a unique answer. We could have no answer. We could have infinitely many answers. So just like in a linear equation. In a linear equation in one variable, one equation in one variable, or kind of like a 1-by-1 system, we can have one unique solution, we can have infinitely many solutions, or we can have 0 solutions. Same idea here. Okay, so we have 2 basic methods for solving linear equations. One is algebraic, the other is graphical. Let's take a glance at the graphical approach first. So if I have 2 equations and 2 variables like up here, I have, let's say, ax plus by equals c and dx plus ey equals f. So here my variables are x and y, and a, b, c, d, e, f are just some numbers. If I look at just this first equation here, I know that I have a list of x's and y's that satisfy this equation, right? Maybe when x equals 0, y equals 3, when x equals 1, y equals 2, and so on. I have a list of ordered pairs that represent a solution to this first equation. Or I can represent those graphically. For my first equation, ax plus by equals c. So I can represent the solutions graphically, or I can represent some of the solutions, some of the ordered pairs in a table. If I consider my second equation, I can write out a table for that one. It's going to have some different ordered pairs. These will be different, choices for x and results for y in my table here, but these will be solutions to this blue equation, dx plus ey equals f. So I have some of those. Or if I plot this blue equation, I might get a line that looks, say, like that if I plot it on the same graph as my green equation. Now, what does it mean to find an ordered pair xy? That's a solution to the system. Well, what that means is that it solves both of these simultaneously. In other words, it might be true that if I inspect my table, I'd have to get pretty lucky here. But if I were to inspect my table, I might notice that, for instance, maybe the same ordered pair occurs in both tables. Maybe, say 1, 2 and 1, 2 appears in both tables. Maybe x equals 1, y equals 2 is a solution to both the green equation and the blue equation. That could happen. I could, again, I'd have to get pretty lucky because when I write out a table, I kind of pick 3, 4, 5 different values out of a whole bunch that I could pick. So, this wouldn't be a very efficient way to solve this, but it could happen. I could imagine that I look at my two tables and I see, oh, I have the same point in the blue table and in the green table. There's the same ordered pair that solves ax plus by equals c and dx plus ey equals f for the same xy combination. That would be a solution. Now, again, like checking tables is pretty inefficient because there's a ton of different solutions. There's infinitely many solutions for the green and for the blue. And I'm expecting like only one of them to match up. So am I going to get a collision whenever I list, 5 or 10 values in each table? It's pretty unlikely. But if I have a graph kind of visually represents like all of the solutions, right? Or at least all of the solutions in a range. So a graph kind of does what each of these tables is trying to do, but it kind of fills in all the gaps. So if I'm looking at, say, a specific point on the blue line, maybe like this point here, that represents an ordered pair that's a solution to the blue equation. That would show up in the blue table. If I'm looking at, say a green point like this one, well, that point shows up in the green table. Now, this green point is not a solution to the blue equation. It's not on the blue line. And likewise, the blue point that I drew over here is not on the green line. So this green point solves the green equation, but not the blue equation. The blue point that I've drawn in the picture solves the blue equation, but not the green equation. So neither of those represents a solution to the system because they solve one of the equations, but not the other. I mean, I suppose I could even have, some other random point here that doesn't solve either equation. But if I want to solve both equations at the same time, I'm looking for a point in this 2D space that's on both lines simultaneously. And that's this intersection point here. So I could get really lucky and find this by inspecting the two tables, but that's pretty unlikely. But if I draw a graph of the two functions, of the two linear equations, either by hand, maybe I can draw the graph very carefully and then maybe estimate the location of this point, say 1, 2, or maybe I can use the calculator and either use a graph to estimate the location of this point or even use some of the built-in calculator tools to give me the answer. The calculator can find the intersection of different curves. So this is the idea. I'm looking for a point that is simultaneously on both of the two lines. I'm looking for a point of intersection between those two lines. And with this geometric understanding, we might see the special cases. If I have two parallel lines that are not the same line, there's no intersection. So no solution. If I have two parallel lines that are the same line, then any point that solves one automatically solves the other. I have infinitely many solutions, right? These are the kind of special cases where I have like a 5% acid and another 5% acid and I mix them together. If I want to get 5% acidity, I can mix them together in a whole bunch of different ways and get 5% acidity. If I want to get 6% acidity out of two 5% acids, that's just not going to happen. There's no solution there. And then there's also kind of a third way in applications that I can get no solution. If I think of this example up here, I'm looking at mixing together different acid. So I want to know what volume of the cooking acid and what volume of the cleaning acid or cleaning vinegar or acid should I mix together. That's A and B. Well, the natural constraint here is they have to be non-negative, right? I can't mix like -5 ounces of the cooking vinegar and positive 35 ounces of the cleaning vinegar. So I might also, maybe I have a situation like this. Let me think, what would this look like? Maybe something like that. And something like that, where I do have a solution to the system. And keep my colors consistent here. But that solution to the system doesn't solve the application problem, right? In this case, I would have like, whatever, x equals -5 and y equals, 35 or something like that. So that those two would sum to +30. That would give me like 30 fluid ounces total, but I'd have to have like -5 ounces of the cooking vinegar and positive 35 of the cleaning vinegar or something. That's not going to work. So I might end up with like a mathematical solution that doesn't meet the practical constraints of the application. So that's a third way that we can get kind of no solution. Not in the strictly mathematical sense, but the mathematical solution we get doesn't make sense from the standpoint of the application. Okay, let's take a look at a system like this one and solve it by graphing. So I'm going to call this first equation the green equation. Maybe I'll zoom in a little bit. I know since I'm in full screen mode, it's probably a little harder for you to see on your screen, so make it a little bit bigger. The first one is the green equation, the second one, the blue equation. And let's graph this by hand, see if we can figure out an estimate for the solution, check it, and then see how we would go about it on the calculator. So for equation 1, I'm looking to graph this, so I'm going to pick 3 points. Maybe I'll pick x equals -1, 0, and +1. When x is -1, I have negative of -1 is +1, and then +4 equals 5. When x is 0, y is 5. And when x is 1, -1 plus 6 gives me 5. And then for equation 2, I'll also get 3 points. I'm going to use these to help me draw the line. So let's see, when x is 0, y, -2y is -6, y is 3. When x is 1, so I have 4 -2y equals -6, or -2y equals -10, y equals 5. And when x is, let's say, -1, I have 4 times -1 is -4. I add that to the other side to get -2y equals -2, and y is +1, right? -2y equals -2, y is +1. That should be right. Okay, so I think I need to go from 0 to 6 or so on the y values, and then just -1 to 1 on the x's. So for my green equation, I have -1 comma 4. I have 0 comma 5. 0 comma 5, if I can count my tick marks right, and then 1 comma 6. So it looks like that is the graph of the green equation. And for blue, -1 comma 1, 0, 3, and then 1, 5. So this is the blue equation. It kind of looks like my intersection is going to be a little bit to the right of x equals 1. Let me try maybe x equals 2. Maybe I won't write it in red yet. Try x equals 2 and see what I get there. So I get 4 times 2 is 8. Minus 2y equals -6, or negative 2y is -14. Y is 7. And from the green, if I plug in 2, what do I get? I get 2 for x. I get -2 plus y equals 5. That's also 7. Hey, look, I found my solution of 2, 7. I found a point that is in both tables. I found a point that is on both lines. Or more algebraically speaking, -2 plus 7 equals 5 is a true statement, and 4 times 2 minus 2 times 7, so 8 minus 14 is -6. That is also a true statement. So there are 3 ways that I can kind of investigate whether something is a solution. Does it simultaneously show up in both tables? Yes, it does. Is it a point of intersection of the graphs of the lines? Yes, it is. If I substitute that ordered pair xy into both equations in the system, do I get 2 true statements? Is the first equation a true statement and the second equation a true statement? Yes, it is. So my solution is 2, 7, and we can see pretty clearly from our graph that there's going to be no other solution. If we go further off to the left, the blue line is just going to get further down below the green line, and if we go further to the right, vice versa. So there's going to be no second solution, and certainly these are not the same line where we'd have infinitely many solutions. So we have our nice case, our condition where we have exactly one solution. Okay, now this was quite a bit of work doing this by hand. Can I leverage my calculator to make this a little more efficient? And the answer is yes. So I would like to get a graph that looks like this one over here, but use my calculator to make this graph. Well, the first thing that I remember is when I'm graphing on the calculator, in my y equals menu, I have like y1 equals y2 equals. I need to solve my equation for y in terms of x. So I rewrite my first equation, y equals x plus 5. And my second equation, I can add 2y over, add 6. I get 2y equals 4x plus 6, or y equals 2x plus 3. So solving both of my equations for y, I get this. Now I come over to my calculator, and one equation I want to plot is x plus 5. I'll put that in y1. And the second equation I want to plot is 2x plus 3. Put that in y2. I note that by default, these little equal signs next to y1 and y2 turn bolded, or they kind of reverse their colors. So I know that those are selected. I know that the calculator is going to graph those. If they weren't selected for some reason, if you clear everything out and then type them in from scratch, it should automatically select it. But if you wanted to deselect, you can hover over the equals, hit enter, and that will turn off the graphing for that function. And then hovering over the equals, hitting enter again, turns it back on. Okay, what window do I want? Yeah, maybe something like this. This looked like a pretty good window. If I was starting from scratch and had no idea, I'd probably start with -10 to 10 on both axes and see where my intersection is, zoom in on it a little bit. But since we have a good idea, we'll start with, say, -2, maybe to +3, and something like 0 to 10. That looks good. -2 to 3 for X, 0 to 10 for Y. Anything in that ballpark is going to look pretty good. And I see my two solutions here, and I can visually estimate that this intersection is at X equals 2 and at Y equals 7. So I would estimate the solution from the calculator to be 2, 7, and then I should do my due diligence and plug in and check. So I'd plug in and check that that is indeed a solution. So that's how I can solve these graphically. I could also go to this above the trace where it says calc. I can go second trace, and I can go down here to number 5. Whoops, a little farther, a little too far, to intersect. Hit enter, and it's going to ask me what's the first curve, and I'll just pick this one, that's fine. What's the second curve that I want to know the intersection between them? Hit enter there. And then what's my guess? It doesn't matter what you pick for guess. For some, if you had something like this, you would want to pick a guess that's close to the intersection you're looking for because there are multiple intersections. That's not the case here, though. So guess, we just hit enter again. And then we see it gives us the intersection of 2, 7, showing us it on the graph. So we can visually confirm, and it did the algebra for us to figure out the answer is 2, 7. Okay, so that is solving by graphing. Really nice idea, but you can see it's kind of a bit cumbersome. I mean, the plus is that we can use the calculator for it. But you can imagine if this was not such a nice point, it would be very hard to visually estimate what it was, even if it was like 2.5, say 2.5, 7.5 or something. It would be really hard to pin down exactly what that was, even if it was something that's a little bit off of an integer like that. So we also have some algebraic methods of solving systems. One example is solving by the addition or elimination method. So what's the idea of this method? Well, I can do things to one equation. I can say, add a number to both sides, or multiply both sides by a number, or subtract a number from both sides, divide by a number on both sides. But if I have like A equals A and B equals B, I can also add straight down, right? A plus B equals A plus B. So that's the idea of the addition method, that I could, in theory, add the left sides together to get, say, 12x minus 9y, and then I can add the right sides together, 6 plus 17. This would be another equation that is a valid relationship for the solution xy, for that solution point xy. That, that coordinate xy that solves both of these simultaneously will also solve this related equation. Now you might say, okay, like this didn't really seem to get us anywhere, and I just have another equation in x and y. But what if we combine these two ideas of being able to manipulate the equations individually with being able to add them together? So maybe I look at this and I say, well, let's just decide to multiply equation 1 by -2. I mean, that's certainly something I'm allowed to do. Maybe we don't see why we're doing that yet, but if I multiply both sides of equation 1 by -2, I get -8x plus 6y equals -12, and I get 8x minus 6y equals 17. That's just the second equation from before. But now if I add these together, actually in this case, what happens? My x's go away. I get -8x plus 8x is 0x. My y's also go away. I get 0 equals 5. In fact, we've ended up with a special case. This is never true. 0 is never equal to 5, no matter which value x comma y we choose. So I can never simultaneously solve these two equations. No solution. Let's maybe try to confirm this on our calculator, see what the geometry looks like here. If I solve the first equation for y, I have y equals, and what would I do? I'd add 3y, I'd subtract 6, so 4x minus 6, and then over 3. So I think that's 4/3 x minus 2. And if I did the same for the second equation, I'd add 6y, subtract 17. 6y is 8x minus 17. Or y is, well, that's 8 over 6x, or that's 4/3 x. And then minus 17/6. So minus a number that's, say, close to 3. Well, we can see the problem here. We have two parallel lines that have different y-intercepts. Or if we went over to our calculator, we would see y equals 4/3 x minus 2 and 4/3 x minus 17/6. And we'll bump our y min down to, I don't know, -5 or so. We can leave the rest of it the same. And we see we have two parallel lines that are not the same line. There's going to be no intersection of these graphs, so no solution. Or if I drew out a table of values, I would never see, for any choice of x that I make, say this one, I would always see a different y value in my two tables. I would never see the same x-y combination in both tables. There's no solution to this one. I have two parallel lines that are not the same line, no solution. I could see that graphically, or I could see that by the addition method. We have an additional method, an additional algebraic method too, which we call substitution. The idea of substitution is kind of similar to addition. In a nicer problem, which we'll maybe see in a couple minutes here, when we apply the addition method, in a nicer problem, what would happen is our 2x2 system, our two equations and two variables, would be reduced down to a 1x1 system, so to speak, but just really one equation and one variable, just a standard linear equation that we can solve with basic linear equation solving steps. The substitution method attempts to do the same thing. So what I'm going to do here is I'm going to solve one of my equations for one of the variables in terms of the other, and then substitute into the other equation. So here I have equations, say 1 and 2. Equation 2 looks like it'll be easy to solve for x. I just have to subtract 3y over. So equation 2 tells me what x is in terms of y. X equals 14 minus 3y. I plug this value for x into equation 1. So instead of negative 2x plus 3y equals 8, I have negative 2 times 14 minus 3y. So this is x, negative 2x, negative 2 times 14 minus 3y, plus 3y equals 8. But now I just have one by one. I just have one equation in one variable, just a standard linear equation to solve. Well, I do my equation solving steps. I simplify both sides to get ay plus b equals cy plus d. Get my variable terms on one side, constant terms on the other side, isolate the variable, and simplify and check. So I have negative 2 times 14 is negative 28 plus 6y plus 3y equals 8. Just multiplying out. I'll combine some like terms. I get 9y minus 28 equals 8. And now I'm in kind of the standard form to start with. I want to isolate my variable term by adding 28 to both sides. 9y is 36. I divide by 9 to isolate the variable itself. 36 over 9 is 4. And I get y equals 4. And to find its counterpart, to find the x coordinate, the x value of that coordinate, I plug y equals 4 back into my equation 2 that I solved for x. So nicely enough, I've already solved this for x. So x then is 14 minus 3 times 4. 14 minus 12 is 2. So I think my solution is x equals 2, y equals 4. And then I would go back, plug in, and check that that actually does work. Is it true that 2 plus 3 times 4, 2 plus 12 is 14? Yes, that's true. Is it true that negative 2 times 2, or negative 4, plus 3 times 4, plus 12, negative 4 plus 12 is 8? That is also true. So this is the solution. Any questions so far? Okay, so let's take a look back at this and see if we can get a solution to this one. See if we can get an answer. I keep saying solution, and we're looking for a solution, and we're looking for a solution in more than one way. Can we solve this problem? Well, I guess I could go a couple different ways here. I could do, say, a substitution where I solve maybe a equals 30 minus b, plug that in down here. I could do that. I could try to graph this. This would probably be pretty messy to graph. I'd have to divide by a bunch of decimals and stuff. That might be messy to graph even in the calculator. That might just be quite a bit of prep work, but I could graph it if I wanted to. Or I could use the addition elimination method. Maybe I'll choose to use that method just because the last one that we saw ended up being kind of a wonky case. So we'll use the addition elimination method here. But as an aside, for practice, when you're going back through and rewriting your notes, if you want to practice this material, when you go through and you say, oh, okay, we solved this one by substitution, maybe choose one of the other methods, graphing or addition elimination, and work out the solution, see if you get the same solution, right? Or this one up here we solved by graphing. Can you use a different method to get the same solution? So that's a good way to practice. You already have the answer there. Try getting that same answer one of the other ways. But this one will use the addition elimination method. So I want to combine the two ideas of the fact that I can kind of add the two equations together, and that results in a third valid equation for the solution point A comma B that represents the answer to this problem. That third equation that I get by adding these two equations together will also be solved by that same solution point. But if I just add them together now, I get like 1.05a plus 1.07b equals some big nasty number. Uh, that doesn't really help me. It doesn't get me anywhere. The reason it's the addition method slash elimination method, well, we want to choose to manipulate one of the equations before we do the addition so that when we do the addition, we eliminate one of the variables. In other words, if I have equation 1 and equation 2 here, maybe I'll choose to multiply equation 1 times, say, negative 0.05. Why did I do that? Well, let's see what happens when we do that. I have negative 0.05a plus a negative or minus 0.05b, and I have to remember to multiply on both sides of the equation. It's easy to forget the right-hand side. So on the right-hand side, I have negative 0.05 times 30. So this is what equation 1 transformed into after multiplying both sides by negative 0.05. We can do this to an equation, right? We can multiply whatever equation by the same number on both sides. It remains a true equation. Let me just copy down equation 2. I'm not going to change that one at all. 0.05a plus 0.07b equals 0.062 times 30. This is equation 2 that was left unchanged. And now I'll choose to add them together. But now when I add them together, I've constructed it in such a way that my a's go away. Minus 0.05a plus 0.05a, there's no a's left over. I have some b's left over, 0.02b equals, and I have positive an amount of 30s and then minus an amount of 30s. So that's like 0.062 minus 0.05 times 30, just factoring out that 30. Or I have 0.02b equals, what is that? 0.012. Did I get my decimal places all right? Looks right. Times 30. Or b is one usually likes making my 4s into 9s, but now it wants to make 0, 1 into something that looks like a 7. So b is 0.012 over 0.02 times 30. Or what can I do? I can bump my decimal place 3 to the right on the top and the bottom. So that gives me 12 over 20 times 30. This 30 is really just the fluid ounces. This tells me that I want 12 parts out of 20 of that 30 fluid ounces to be, what was it? Cleaning vinegar, to be type B. Or 30 over 20 is 3 halves. 3 halves of 12 is 18 fluid ounces. So we want a proportion of 12/20ths of our resulting solution to be from the cleaning vinegar, or that represents 18 fluid ounces. And if B is 18, well, we pick one of our equations. Equation 1 is the easiest to deal with. A plus 18 equals 30. So that's that A has to be 12. So I want to mix 12 ounces of my cooking vinegar, the less acidic, with 18 ounces of my cleaning vinegar, the more acidic. That will make a total of 30 ounces, 30 fluid ounces, of a solution that is 6.2% acidic. Does this kind of make sense? Well, if I mixed equal parts of cooking and cleaning, I would get a 6% acid by volume. I want a little more than 6% acidity. I need a little more cleaning vinegar than cooking vinegar. B should be a little more than A. So this does mesh with my intuition. As an exercise, since we're about out of time, we'll leave this as an exercise. as an exercise, instead of trying to find a 6.2% acid solution, that 6.2% coming in here, try to find an 8% acid solution. Now, as a little hint, you will get a mathematical solution, right? Whether you use the calculator or you go this route, you will come up with an ordered pair. You will come up with two numbers for A and B that when you substitute in will solve these equations simultaneously. That doesn't make sense though, right? Because how can I get an 8% solution when I only have 5 and 7% to mix together? So why is it not a solution to our application? So find the mathematical solution and ask yourself why that mathematical solution doesn't represent an actual solution to the application, and such a solution to the application would be impossible. Okay, so that's an exercise for next time. Maybe we'll quickly go through that answer next time and then continue on with some more examples of solving linear systems and applications. Let me stop the recording here.